Hello, this is video 82. I'm going to talk about energy in simple harmonic motion. This is going to be a brief video, and it's going to be a good review of the things that we've been talking about. So let's look at the kinetic energy of a mass on a spring, because we know that a mass on a spring undergoes simple harmonic motion. What's shown in this picture is various positions of the mass. So it's starting here from a stretched position, and then it goes to the left toward the equilibrium position, which is right here. So this is x equal to 0. And then it keeps going, and then it stops here at the maximum compression. And then after that, it's going to go back to the right. So we know that when an object is at rest, that it has no kinetic energy, because kinetic energy is 1/2 mv squared. So this means that as far as this diagram is concerned, if we label these A, B, C, D, and E, then it means that the mass is at rest over here. So Ke is equal to 0. And then the mass is at rest over here. Whenever you have maximum stretch or maximum compression, the object stops because it's about to go the other way. So that's all we're saying here, where the kinetic energy is 0. And then at the equilibrium position, kinetic energy is a maximum value. We talked about in the previous video that at the equilibrium position here, this is when the object is going its fastest, because it has been speeding up from a rest position. It speeds up as much as possible here, and then it starts slowing down as it goes more to the left here, because that spring force starts to push it the other way, because it's being compressed here, so that spring force pushes it back. So if it's going as fast as possible in the equilibrium position, that means that it has Ke max in the middle. And now we can do the same thing and look at potential energy. Potential energy, when the object is at rest, the potential energy is a maximum value. So we just talked about the object was at rest at these extreme positions. So at these positions, PE, the spring potential energy, is equal to 1/2 Ka squared. We have replaced the usual x for A because x is that displacement from equilibrium, and when it's at its maximum displacement from equilibrium, that means x is equal to A, the amplitude. So, whereas the object had no kinetic energy at the extremes, it's going to have maximum potential energy. So PES max at the extremes, 1/2 Ka squared. This means that when the object is going through the equilibrium position, it has no potential energy because there's no displacement from equilibrium. X is 0. This whole term here goes to 0. So hopefully from what we're talking about, you can see that there's definitely something going on between potential energy and kinetic energy. And this has to do with conservation of energy. If we go back here, if it had no kinetic energy here, then it had maximum potential. As it lost all of the potential, it gained kinetic. So this is the same thing that we've seen when you're dropping an object. It starts with a bunch of potential, and it all goes to kinetic. Here it starts with potential, it goes to kinetic at the middle, back to potential here, and so on. So what we can do here is we can look at conservation of energy, and this tells us that the maximum potential energy must be equal to the energy at any other time. So what I'm saying here is I'm looking back at this picture, and I'm saying, okay, at this location here, it only had spring potential energy. It didn't have any kinetic energy. But energy is not lost or created or destroyed anywhere. So if this is the total amount of energy that it has at this position, well, at any other position, it's still going to have that same total amount of energy. Now, at any other position, except for the middle part, at any other position in between, such as this position right here, we can say at this position that there is some displacement from equilibrium, that's x, and there is some velocity v. So at this location, the energy of this object is going to be 1/2 mv squared plus 1/2 kx squared, where we're not using Vmax, we're not using A for x, but the energy is still the sum of those two energies, and that must be equal to the total energy at the initial position. So that's all that I'm saying in this equation right here. The energy is not changing. If you do a little bit of algebra and you solve for the velocity, you'll actually get this expression here. And what this expression tells us is that if we know the amplitude, the maximum position of that mass from the equilibrium position, and then if we know the spring constant and the mass of the object, then if we know the position of the mass anywhere throughout its motion, if we know x, then we can figure out how fast it's going. This means that we're not limited to just finding the velocity of the mass at the equilibrium position. We can find it anywhere. And just to see that this equation makes sense, let's assume that we are at the position x equals to a. Look and see what happens when you plug in a for x. When you plug in a for x, you get a squared, you get a squared minus a squared, which is 0. You get 0 when x is equal to a. Can you see that that agrees with our pictures? When x is equal to a, that's right here, v is indeed equal to 0. So that's it for this video. We're just showing you that energy is conserved, and that does allow us to derive an equation to give us the velocity of this object at anywhere. So now we have another equation that gives us the velocity as a function of time, and now we have a velocity as a function of position.